Hello everyone and welcome back to Math 127 Pre-Calculus 2. Alright, so in the previous section, we focused on coordinates and triangles. Now we will introduce a powerful mathematical tool called a vector. So unlike with ordinary numbers, we know that vectors have both magnitude and direction. So making them useful in, for example, the physics, engineering, navigation, and in many real-world application. Okay, so let's go ahead and begin. So by the end of this lesson, we should be able to know or learn this concept. Okay, all right, so starting with the vectors. Okay, like I mentioned, a vector is a quantity that has a magnitude and the direction. Okay, so example for this, for instance, we have the velocity, we do have the force, and then of course the displacement. So this is different from the scalar quantity, which has magnitude only. All right. Okay, so we will also learn about the directed line segment, the initial points, terminal points, and the vector magnitude. As you can see here, this is an example of a vector wherein you see here the initial point where we are starting, and then of course the terminal point where the direction is pointing at. Okay, so again, a line segment to which direction has been assigned is called the directed line segment. We call point P the initial point, and then the point Q as the terminal point. And so we denote the directed line segment by those 2 points there, and then of course the symbol. So how about the magnitude? So the magnitude of the directed segment PQ is its length. So we denote it with those double vertical line enclosing the name of that vector. So geometrically, a vector is a directed line segment. Okay, so in geometry usually we call them as a ray. Okay, all right, so how do we write them on a paper? So we know that if you'll notice on the guided notes there that there are letters here that are printed in bold. Okay, so when they are printed in bold, that means to say we are referring with a vector. So let's say, for example, vector V, vector W. But how we write them on a paper, make sure that you do have those symbol, those directed line segment above those line. Now, how do we represent them in print? With, for example, the magnitude. So again, we are using those double vertical line enclosing those names of the vectors. However, if you're going to write them on a paper, make sure again above those letters must have the directed line segment. Okay, so now let's move on with the equal vector. So now, when do we say that the two vectors are equal? So you have to remember that we can only say that the two vectors are equal if they have exactly the same magnitude and same direction. Okay, so and then we write it as the vector V is equal to the vector W. Okay, so let's go ahead and look at the following illustrations here and see how they are said to be equal. Okay, so the first example, so again, make sure same magnitude and same direction. So that means to say that if I'm going to, let's just say, if I'm going to draw this exactly like this, if I'm going to move this, slide this to vector W, it should overlap it at exactly the same diagram of vector W. And as you can see, it really is overlapping on vector W. Okay, vector V, vector W. They are exactly the same. So they do have exactly the same magnitude, and then they do have exactly the same direction. As you can see there, they are pointing on this direction, both of them. Okay, so we can say that they are equal. Okay, next for the vector V and W. As you can see here, they may have exactly the same magnitude. However, like I've said, if I'm going to slide this vector V to vector W, they do not overlap. Okay, so that means to say that they may have exactly the same, again, magnitude, but they do not contain the same direction. That means to say that these two vectors cannot be called as equal vectors. Okay, so next one. So next one is, obviously these two vectors looks this has exactly the same magnitude. Okay, however, in this case, they do not have exactly the same direction. They do have opposite direction, so we cannot also say that they are also equal vectors. And then lastly here, again, if I'm going to draw vector v, so as you can see here, if I'm going to slide this, okay, it doesn't match they don't match their magnitude, although their direction matches. However, the magnitude are not equal, so therefore we cannot also say that these two vectors are equal. Okay, so that's how we visualize them. Okay, so how do we prove that the two vectors are equal algebraically? Okay, so let's say, for example, these 2 points right here. Okay, so let's say we have here the vector u and then the vector v. Okay, so what we are going to do here is, first we're going to prove that these two vectors are equal. So what method are we what formula do we use in order for us to show that their vectors, their magnitudes are equal? We use the distance formula from algebra. Okay, and then as you can see, they are pointing on the same direction. However, we need to make sure that they do have exactly the same inclination. So how do we prove that? Okay, in algebra we have what we call the slope formula, wherein you measure the inclination of the line. Okay, so we are going to use those two formula in order for us to show that these two vectors are equal. Okay, and then later on we're going to prove more of their direction. Okay, for now we will be proving them the magnitude and then their inclination, making sure that they do have exactly the same slope. All right, so let me go ahead and start with vector u. Okay, so we have here the vector u, so I'm gonna solve the magnitude of vector u. So let's say this is my x sub 1, y sub 1, and then x sub 2, and then y sub 2. So we have here a formula from the distance formula, that x2 minus x1 squared plus y2 minus y1 and then squared. Okay, and then we know that when we substitute this value, so we have there the x2 is -2, and then x1 we have here -5. According to the formula, it must be the opposite of x1, so that's gonna be +5 squared instead of the -1. And then plus the y2 we have here 6 minus y1, it's +2, that becomes now a -2, and then square. All right, simplifying this, we now get a 3 squared plus the 4 squared. So now we get a 9 plus 16. So now we get a radical 25, which is simply 5. Okay, all right, now let me go ahead and move on with vector v. So once again, I'll treat this as my x sub 1, y sub 1, and this is x sub 2, and then y sub 2. So magnitude of vector v. So now we'll have here that x sub 2 is 5 minus x sub 1 is 2, and then square, plus y sub 2 we have 6, and then y sub 1 we have there, y sub 1 there is 2. That becomes -2. Okay, all right, so now we now simplify, so we get a 3 squared plus 4 squared. So that's gonna be now 9 plus 16, which is now equal to radical 25, which gives us a +5. Okay, so as we can see now that the magnitude of vector u, it's just equal to the magnitude of vector v. Okay, but we are not yet done. We cannot yet conclude unless if we have algebraically proven that those two vectors have exactly the same inclination. Okay, so like I mentioned, we are going to use, to measure their inclination, is to use the slope formula. Okay, so for the slope formula here, we have, let's say m is equal to y2 minus y1 over x2 minus x1. Okay, so once again, this is one way to show that vector u and vector v have the same direction. Okay, again, is to find the slope of the lines on which they lie. Okay, all right, so let me go ahead and start with the vector u, slope of the vector u. So we have there the y2. The y2 is 6, and then y1 is, that becomes -2 because of this negative sign before y1. Okay, x2 is -2, x1, that becomes +5. Okay, so this is now equal to 4 over 3. Okay, now I'll move on with the vector v, the slope of vector v. So again, y2, I did have 6 minus y1 is 2 over x2 is 5, y1 is 2. Okay, now simplification. So we now have here 4 over 3. Okay, so as you can see here, they do have equal measures. So in this case, I can now say that, and okay, the slope of vector u is equal to the slope of vector v. Okay, so now I can now conclude that since the vector u and v have the same magnitude and direction, then therefore I can now say that vector u is equal to vector v. Okay, all right, so since the two magnitudes are equal and the two slopes are equal, they do have the same directions, then therefore I can say that these two vectors are equal. All right, moving on to, okay, the scalar multiplication. Okay, so next, we now multiply vectors by real numbers. So remember, when multiplying by a positive scalar, the magnitude changes and the direction stays the same. So when multiplying by a negative scalar, the magnitude changes, the direction reverses. Okay, so this concept helps us stretch, shrink, and reverse vectors. Okay, all right, so as you can see here, we do have the first one. If we have here the vector v, multiplying that vector v by a scalar 2, that means to say you are stretching it. Okay, so but then again, you still have exactly the same direction. So as you can see, it has twice the magnitude of the original vector. Okay, now the other one here is making it a half. Okay, so if I'm going to slide this, this is like half of this vector v. And then the other one here is we are stretching it by -3 over 2. But then again, we are, since this is negative, as you can see, the direction here reverses. Okay, all right, moving on to okay, so moving on to the vector addition and subtraction. Okay, all right, the result there. Okay, so we will learn how to add vectors geometrically using the head to tail method. So the resulting vector is what we call the resultant vector. So for subtraction, we simply have the, for example, vector v minus the vector u. So it's like having, okay, so if you have vector v minus vector w, so this is like saying vector v plus the negative sign of opposite of vector w. Okay, and then we will interpret the result geometrically. All right, so in this case, as you can see, okay, so for example, let me go with a blank portion. Okay, okay. All right, so let me separate this three vectors up here. So, okay. So for example, this is our vector u, and then we have here the vector v. Okay. All right. Now, for us to do the what we call the head to tail method. Okay. So, for example, if I'm going to have this vector u right here, and then we know that this would be our initial point and then the terminal point. So, all we need to do is to connect the the terminal point of the first vector and then the initial point of the second vector. And then after that, oops. Okay, and then after that, we just need to connect the initial point right here from the first vector to the terminal point of the second vector. So again, connecting those 2 points. Oops. Okay, let me use this as okay. So now connecting these two. So as you can see there, okay, I have connected again the initial point of the first vector and then the terminal point of the second vector. So this line right here is what we call the resultant vector. Okay, that u plus v again gives us the resultant vector. Okay, now another illustration here would be this one. Okay, so for example, if you have that okay, so v minus, or the vector v minus the vector u. So let me just go ahead and start drawing those original vector here. So these are the given. This is vector v. Okay, and then this is vector u. Okay, so this is vector v and then vector u. Okay, so if you're going to subtract, okay, that vector v and then minus vector u, so we are good with vector v, so nothing to do there. However, with the vector u here, we need to change its direction. So instead of going to that direction, I am going to draw, okay, exactly the same magnitude but on a different direction. Okay, and so I will now be, so this is now a negative vector u. Okay, so now I will connect this. Like I've said, I will have the head to tail method. So I'm going to connect this on this portion right here of vector v. Okay, all right, and then after that, I can now connect the initial point of the first vector and then the terminal point of the second vector. So I will now have this. Okay, all right. Okay, so now this is now we have here the vector v minus the vector u. Okay, all right, so there you go. So that would now be our resultant vector. Okay, all right, so this is head to tail. We can actually also use the parallelogram method here. So parallelogram method, simply you just need to draw exactly the same vector over here, just the way we have illustrations here. So vector v and then vector v as well here. And then for the negative vector u, okay, it's like creating a parallelogram here. And then after that, you just need to connect or create a diagonal, and that would now be your resultant vector. Okay, all right, now let me go ahead and move on with this example. Okay, so for example, we have the vector w and then vector v. Okay, so let me just go ahead and move that. Okay, I'm just gonna go ahead and do head to tail method. Okay, So we have here the vector W. So I'll start with vector V. I cannot draw exactly how it is because they don't contain exactly the same measurement of the grid line here. But okay, so let me go ahead and try. Just be counting the number of units here. We have 1, 2, 3, 4, 5, 6. Okay, let me go ahead and draw here, anywhere here. Okay, like I've said, the location does not matter. So we have 1, 2, 3, 4, 5, 6. Okay, so this is vector V. Okay, next one, I am now gonna draw vector W plus vector W. So I have here, okay, so we have 1, 2, 3, 1, 2, 3, 4. Okay, so I have here 1, 1, 2, 3, 1, 2, 3, 4. Okay, so this is now the vector W. Okay, all right, so now I can now connect the first vector that I have drawn here, the initial point, and then the terminal point of the second vector, which is the vector W. Okay, so this is now vector V plus the vector W. Okay, all right, so next one, how about vector V minus the vector W? All right, okay, so first let me draw vector V. Again, 1, 2, 3, 4, 5, 6. Okay, so let me draw vector V on a 6 unit. 1, 2, 3, 4, 5, 6. Okay, vector V. And then vector W, in this case, instead of going to that direction, I will go in opposite direction because of this negative sign. Okay, so once again, I counted this as 1, 2, 3, and then 1, 2, 3, 4. Okay, so I'll have here 1, 2, 3, 1, 2, 3, 4. So this is now, okay, the negative vector W. Okay, all right, so now I can connect now the initial to the terminal point. So this is now the vector W minus the vector, vector V minus the vector W. All right, so next one, how about the 1/2 of vector V? Okay, so 1/2 of vector V, meaning to say that we will just be dividing this half. So we'll have here 1, 2, 3, 4, 5, 6. So instead of 6 units here, I'm going to draw the line or the vector by 3 units. Okay, so that's gonna be 1, 2, 3. Okay, so this is now 1/2 of vector V. Okay, so there you go. That's how we do it on a plane. Okay, all right. Now moving on to, okay, so we have here the I. Okay, so we do have here the I and J. So this is the vectors in the component form. So now we'll move in, now we'll move into a rectangular coordinate. So we will be introduced by the unit vectors, such as the vector I and then the vector J. Okay, so and we are going to write the vectors in the form of the vector V is equal to A and then vector I plus B and then vector J. Okay, where again, where A and B, where A and B here are the horizontal and then the vertical component. Okay, and also for the magnitude formula here, of course, the magnitude of vector V, for example, so this would be the square root of the 2 horizontal and then the vertical component, square of each of those. Okay, all right. Okay, so this is just another illustration here wherein we see that, as we can see here, that A is the scalar multiple of vector I, which is the horizontal component. And then, of course, the B here is the scalar multiple of vector J, which is the vertical component. And then, again, using what they call this, the hypotenuse here, or the resultant vector here would be, again, this multiples the multiple of vector I plus the multiple of vector j. Okay. Okay, let's take a look at this example. So for example, we want to sketch a vector v is equal to 3 and then vector I minus 3 vector j. Okay, so like I mentioned, this is our horizontal component, okay, which is this. And then the vertical component, which is once again the y-axis. Okay, all right, so sketch the vector 3i and then minus 3j. So that's going to be 3i, so it would be here, and then 3j down here. Okay, that would be the point. Okay, so this would now be our vector. Okay, all right, so that is now our vector v. Okay, now let's go ahead and find the magnitude. So we'll have here the magnitude of vector v is equal to, we said that this would be the square root of a square root of a squared plus the b squared, and we know this is a, that 3 squared plus the negative 3 squared. So this is now 9 plus 9. So we get here radical 18, which is, again, square root of 18, that's going to be 3 radical 2. So this is now the magnitude of vector v. Okay. All right, let's have another example. If you get the concept here, then you can pause the video and then work on with the next example. Okay. All right, I hope you were able to practice this. Okay, so let me go ahead and answer this, the vector or the magnitude of the vector w. Okay, so I have here the horizontal component, the vertical component. So now we have a is 2 and then negative 5 down here. That would be the point. And so the vector would look like this. Okay. All right. So now this is now the vector w. Okay. So again, finding the vector w, we use the formula radical a squared plus b squared. And so we have here that 2 squared plus the negative 5 squared. So we have 4 plus 25, which gives you a radical 9. And then the square root of radical 29 is already in simplest form. So this would now be our final answer. Okay. All right. Okay, so now let's go ahead and move on with the operation using the vector I and vector j. So once vectors are written in component form, the vectors operations become algebraic. Okay, so let's go ahead and practice the addition, subtraction, the scalar multiplication, and then the magnitude calculation. So this is often much faster than drawing actually vectors, right? Okay, so but however, let's go ahead and illustrate that. Okay, so we have here that point P, which would be our point 1, which is our initial point. Okay, do not switch those two. And then the second point, which will be our terminal point. So we have here that vector v is x2 minus x1, and then of course vector I. And then we have here the y2 minus y1, and then the vector j. Okay, so for example, let me go ahead and plot this point first. So point 1 is negative 1 and then 3. So we have negative 1 and then 3, negative 1, 3. Okay, let me just. Okay, that is our initial point. And then our terminal point would be 2 and then 7, 2 and then 7. So this is 5, 6, 7. Okay, this is at negative 1 and then 3. And then this is at 2 and then 7. Okay. All right. So now let's move on with we're going to write the vector v in terms of vector I and vector j. Okay, so we know that this would be our x1, y1, and then this is our x2 and then y2. Okay, so we will just be following exactly this formula. So vector v now is equal to x2 is 2 minus x1, so that's gonna become 1, simply 1, and then the vector I, and then plus y2, we have 7 minus 3, and then vector j. So this is now 3i plus 4j, and that would now be our vector v written in I and j component. Okay, all right, so next one. Okay, so how about this one? All right, so again, if you are able to do this, then you can go ahead and work on with letter B by pausing the video, and then after that you compare your answer. But by the way, if I'm going to, let me just go ahead and play a little bit in here. So if I'm going to slide this, okay, so we see that this is the horizontal component and vertical component. That means to say if I'm going to slide this, okay, it must be on 3 and then 4 component. Do you see that? Okay, that point. Okay, so there you go. I just showed you the, okay, there you go. Okay, so that is the relationship between it. Okay, so if you're going to draw this on the origin, that the initial point would be at the origin, then therefore this 3, 4 would be your terminal point. Okay, all right, now moving on to the next one. So again, I'm just gonna go plot this point first. We have here negative 5 and then positive 6. So negative 5, positive 6. That is our initial. So negative 5 and then 6. And then we have here negative 2 and then 1. So this is now our, oops, let me just go draw that again. Okay, so this is our, again, vector v. All right, so once again, if I'm going to slide this this initial point to the origin, we should be getting the component of I and j once we have written this in terms of I and j. Okay, so vector v, so that's going to be equal to, so x2, okay, so let's say this is our x1, y1, x2, and then y2. Oops, okay, y2. Okay, so we will just be doing exactly how we did from the previous example. So x2, we have the negative 2, and then plus 5, okay, square, and then plus we have here the, oops, why did I need, okay, not square, that is from the distance formula. Okay, so we have here 1 minus 6 j. Okay, so there you go. We have here the 3 and then the negative 5. Like I mentioned, if we're going to slide this going here, and then we should have that 3 and then the 5, the negative 5 for the terminal point. Okay. All right, now let's go ahead and move on. Okay, like I mentioned, we are going to now to practice the addition, the operations, okay, in terms of the vectors. Okay, so we do have here those properties given here for the adding and subtracting vectors in terms of I and j. So if you have vector v plus the vector w, you only need to add their component for, of course, vector I, and then for the j component. Okay, and that is similar with the subtraction. Okay, so for example, if you have vector v and then vector w, so let me just go ahead and add that. Okay, so we have here that under the horizontal component, we have the 7 and then the 4. So all you need to do is to add them. And then vector I. Okay, plus for the j component, have 3 minus 5. So this would now be 11 I component. Okay, and then, oops, that's going to be now minus 2j. Okay, so this is now vector v plus vector w. All right. Okay, so same way with v minus vector w. Vector v. Okay, so v is 7 and then minus 4 for the minus w plus, okay, so we have here 3 minus w, so that's going to be positive 5 j component. Okay, so now we have here 3i plus 8j. Okay. All right, so there you go. So that would now be our example there. Okay, so remember, if for example, if you do have those scalars, so all you need to do is to multiply that scalar to each of those components. Again, to each of those components, okay? All right, now let's again work on with the next one. So let's say we have here 8 times the vector v, okay? So that means to say you just need to multiply this 8 to each of the vector, to each of the vector component of vector v, okay? So that's going to be vector v, 8 vector v. So you will have 7 times 7 times the 8. You'll have 56 I, okay, plus 8 times 10. So we have 80 and then j hat. Okay, there you go. Now moving on to 2 vector times vector v minus 5 vector w. Okay, so first I am going to work on with vector v by multiplying 2 to each of those components. So I'm gonna have 14 I and then 2 times 10 we have plus 20 j minus we have here, oops, okay, I can make it this plus. And then, okay, the negative 5, okay, I'll multiply to each of these components. So that's going to be negative 25. Well, you can move it outside the parentheses. And then after that, you just need to, you know, distribute the negative sign. And that's okay. So we have here positive 15. J. Okay, so now I'm now going to go combine those components. So we have here 14 and then minus 25. So that's going to be negative 11. And then 20 plus 15, so plus 35. Okay, so this is now equal to 2v minus 5w. Okay, all right. Next and the last one. Okay, we are looking for the magnitude of C. Okay, but first we will simplify the inside. Okay, the w minus 2v. Okay, so w we have, well, exactly the same thing. So we will have that 5i minus 3j. Okay, plus, okay, so I'm just gonna go ahead and multiply 2 to each of this. So now we have here 14 I, oops, and then we have 10. Okay, I did have the negative sign here. Okay, all right, and then minus, we have a negative 20j. Okay, so now let's simplify. So we have 5 and then negative 14 is negative 9 I. Okay, negative 3 and negative 20 is negative 23j. Okay, and then after that, all we need to do is, I'll go back with that one. Okay, 2b. Okay, so now I will now go to what they call this, the distance. Okay, so we will have here a squared plus b squared. Okay, so we have here that negative 9 squared plus negative 23 squared. Okay, so we have here 81 plus 23 squared is 529 plus 81, so we get 610, and then the square root of this will have 610. We get exactly the same thing. Okay, so we have here the vector W minus 2 vector V. Okay, so there you go. All right. All right, now moving on to, now we have what we call the zero vector. So the vector, okay, so the vector whose magnitude is 0 is called the zero vector. The zero, okay, so the zero vector is again a sign it's a sign no direction. So it can be expressed in terms of vector I and vector j using this equation. So we have there 0 is equal to 0 I plus 0j. Now we also have some properties that we can take note of, okay, the properties for the vector addition, that according to these properties that u plus v is the same thing as switching their position, okay, for the associative property. Even though they don't have the same groups here, they will arrive with the same value, okay. And then additive identity, adding a zero vector that won't affect the value of the vector itself, which is in this case vector u. And then we have here the additive inverse. If you're going to add its opposite vector, then it gives you a zero vector. Okay, same thing, we do have here some properties of the multiplications, the scalar multiplication. So we do have here the vector u and then v, u, v, and then w are the vectors. So we see here some associative property, distributive property, multiplicative property, multiplication property of 0, and then the magnitude property. Okay. All right, now moving on to the unit vector. So again, unit vectors is defined to be a vector whose magnitude is definitely equal to 1. Okay, that is why it's called unit vector. All right. Okay, so let's have an example of the unit vector. Okay, so for instance, in this case that we want to find the vector in the same direction. So we have the vector v is equal to 4i minus 3j. So I'm just going to go ahead and follow the formula of the unit vector, that vector v, for example, over divided by its magnitude. Okay, so in this case, we first find the magnitude of vector v. So that's going to be a squared plus the b squared. So a squared here is 4, so 4 squared plus the b squared, we have a negative 3 squared. So which is now radical 16 plus 9, so which gives us a radical 25, which is 5. Okay, now I'll go back with this big formula here. So then now the unit vector, so now we have vector v over the magnitude of vector v, which is now equal to 4i minus 3j over 5. Okay, I will just be distributing the 5 there. So this will now be 4 over 5. Okay, and then minus 3 over 5, and then j component. Okay, all right, so this would now be our equation. But let me just go ahead and check and see if the magnitude of this vector is 1. Okay, so by again going back with this formula right here, so I'm gonna have a and then the b. Okay, so we'll have here the 4 over 5 squared plus the negative 3 over 5 squared. Again, I'm just proving that the magnitude of this equation is now equal to 1. Okay, so we can see that 16 over 25 plus 9 over 25. Okay, now we see a 25 over 25, which gives us equal to 1. Okay, yeah, so it's correct. Now, that this equation is once again a unit vector with the same direction. We did not change the direction. Okay, all right. Now, moving on, again, you can pause the video and then do this second example as a practice part on your end. Okay, it has exactly the same process here. Okay, let's do that again. So, again, first step is to find the magnitude of vector v. All right, simplify. Okay, all right, so now we have there the magnitude 13. Okay, so now I'll go here now, vector v. Okay, and then I will just be distributing each of this. Okay, now let me go ahead and prove that the measurement or the magnitude of this would be equal to 1 by using the distance again. All right, okay, so there you go. Yeah, so this is now the unit vector of vector v. Okay, all right. So writing vectors in terms of its magnitude and direction. So we do have here the formula. So we have the vector v is equal to the magnitude of vector v, and then cosine the angle theta, and then of course the vector I plus the magnitude of vector v sine angle theta, and then the magnitude, or I mean the vector j. Okay, all right, so given here once again the angle theta, and so this vector here defined as this statement. All right. Okay, now moving on to, okay, solving that. So let's go ahead and write the vector v in terms of I and j, whose magnitude of vector v, whose magnitude vector v and then direction of the angle given here. Okay, so we will just be following exactly the formula that we have here. So let's say vector v, okay. So it says there that the magnitude of vector v is cosine theta, and then I hat, okay, and then plus magnitude of vector v, and then sine theta, and then j. All right, so we will just be substituting those value, and then cosine 30 degrees, and then I plus, this is 16, sine 30 degrees, and then j. Okay, all right, so we know that for the 30-degree angle here, okay, so for the cosine, so if we're going to create once again a special right triangle here, opposite the 30 degrees, that y is equal to 1, and then adjacent with 30 degrees is the radical 3. Okay, so with that, cosine is adjacent given that the hypotenuse is 2. So therefore, the adjacent over hypotenuse here is radical 3 over 2. Okay, and then plus 16 times the sine 30, so that's going to be 1/2, and then j hat. Okay, simplifying this, we now have here 8 radical 3 plus 8, and then j. Okay, so this is now vector v. All right. Okay, now moving on to the next item here. Okay, so similar with this one, we will do exactly the same formula. So vector v, for example, is equal to, again, the magnitude of vector v is 8, and then cosine 225 degrees plus 8 sine, and then sine 225 degrees, and then j. Okay, so now we know that for the 225 degrees, so that's going to be in quadrant 3. Okay, the 225 degrees. And if we're going to look at a special right triangle here, this is a pi over 4 because, again, sorry, that not pi over 4, but okay, so in degree form, this is 45 degree. Okay, so 45 degrees, so that means to say that x here is equal to the negative radical 2, and then the y here is negative radical 2, and of course given that the hypotenuse is 2. Okay, so therefore this is 8, and then we have here the negative radical 2 over 2 plus 8 sine 25 degrees, so I keep on missing that. Okay, so sine 225 degrees, so that's going to be negative radical 2 over 2, and then j hat. Okay, simplifying this, we now have a negative 4 radical 2 plus, that's now becoming a negative sign, negative 4, and then we have radical 2 j hat. Okay, so this is now our vector v. Okay, next example. Okay, so let's go ahead and use the parallelogram rule to find the magnitude of the resultant of the resultant force for the two forces shown in the figure. Okay, so we have here that the first force here we have 19 pounds, and then we have here the 16 pounds, and then we have an angle here which is 106 degree. Okay, so what I'm going to do here is I am going to use a calculator. Okay, so no, find the magnitude, yeah. Okay, of the resultant vectors. So we first apply, okay, like I've said, for the parallelogram. Okay, so now let me just go ahead and draw like a parallelogram here. So let me move that on this side. Okay, and then I'm going to draw also the same. Okay, all right, so we know that this is 19 pounds as well, and then this is 16 pounds. Okay, so drawing the resultant vector would be this. So this would now be our resultant vector. Let me denote that as uppercase R, okay? So according to the parallelogram, they said that if you do have a consecutive angle there, then they sum up into 180 degrees. So that is 180 minus 106. So that's going to be here is 74 degrees, okay? And so if that's the case, then if I'm going to draw a diagonal there, according also to the parallelogram in geometry, that means to say it bisect the angle. So if that's the case, then the angle here would now be 100. Okay, so 106 degree. Okay, divided by 2. Okay, so we have here 53 degree. Okay, over here 53 degree. Okay, all right, so next one, so what I'm going to do now is so since we already have those two values here on these two sides right here, and then we do have the value for the angle here, and then well, actually, even though we don't have those measurements, I realized we actually do not need that. We only need this measurement right here. Why? Because we see here a triangle that is an SAS triangle. And you have to recall from section 6.2, if you have SAS triangle, then you can apply the formula of the cosine law, okay? That, let's say for example, this is an angle, okay? So that would be that r, this should be r squared, but I'm just going to go ahead and write it as a square root on this side, okay? Removing that square of the formula under the cosine law. Okay, so I will have now the two measurements of the two sides, which will now be 19 squared plus the 16 squared minus 2 times 19 times 16, and then cosine, and then that angle opposite to that side that we are solving, so which is 74 degrees. Okay, so now let me go ahead and put this everything on my calculator. So we have here the square root of 200, square root of 19 squared plus 16 squared minus 2 times 19 times 16, and then times cosine 74. Okay, all right. So now what I have here now in my calculator, I do have there 21.19. Let me just go ahead and express my answer in to the nearest tenth. Okay, so r here is approximately equal to 21.2. Okay, so therefore the resultant force here is 21. So the resultant force is approximately equal to 21.2 pounds. Okay, there you go. Okay, now let's go ahead and move forward with the next example. Okay, so for the second example, we do have here from north 45 degrees, 45 degrees from east of north. Okay, from north to east 45 degrees. So the vector points are northeast, so we are going to use now that vector v, okay, which is equal to okay, so let me just go ahead and draw that first for you. Okay, so it says here the jet stream is blowing at 60 miles per hour in a direction of from north 45 degrees to east. Okay, so express the velocity as the vector v in terms of I and then j. Okay, so therefore we do have here that 60, okay, it blows on that direction, okay, from north to east. Okay, so that's gonna be, we know that, well, this 45 degree refers onto this angle, but then again, that 45 degree also has, I mean, the other half here is also 45 degrees. Okay, so therefore our angle theta here from the formula that we are going to use is also 45 degrees. Okay, so let me use the formula, write the formula first. Okay, so we have here the magnitude of vector v cosine theta plus the magnitude of vector v sine theta and then j. So this is now is 60 miles cosine 45 degrees, and then oops, this is I, okay, all right, I, okay, plus 60 sine 45 and then j. Okay, so evaluating the cosine 45 degrees, I'll go back with this illustration right here. We know that if it is a 45 degrees, then therefore x here is equal to radical 2, y is radical 2, given that the hypotenuse is 2. So if that's the case, then we have 60 times the radical 2 over 2, and then I plus 60 times radical 2 over 2, and then j. So now simplifying this, we get now 30 radical 2 I plus 30 radical 2 and then j. Alright, so I apologize. I think it was cut. Okay, I didn't realize my recording was stopped. But anyway, I think I have stopped where I was solving what do you call this, the equation of the vector v here, wherein I just substituted. I went back to this special right triangle. I'm not sure where it was cut, but anyway, I'll go back. So we'll have here the special right triangle here. Like I mentioned, that we do have here 45 degree. So we know that x and y are radical 2, and so evaluating cosine 45 degrees radical 2 over 2, sine 45 degrees radical 2 over 2. So now we get here that the vector I and then the vector j. So simplifying this, we get the 30 radical 2 I plus 30 radical 2 and then j. Okay, so you can also express your answer in approximation depending on how the problem wants you to write. But since the problem is not telling us how to write our answer, either exact or approximation, so I'm just going to go ahead and leave our answer like this. All right. Okay, so now moving on to the final example, okay, because after that, that would be your part, which is the checkpoint part. So first, we need to illustrate that so we can clearly visualize what we are solving here. Okay, so let me go ahead and draw that. So let's say this is my y and then x-axis. Okay, so let me go ahead and start with the first force. Okay, so it says here that F1 has a magnitude which is 30 pounds, and so it is from north to east. We do have here 10 degrees. So let me just go ahead and draw that. So it looked like this. Okay, so this would now be a 10 degree. Okay, I'm not gonna go write a lot of information here, so to avoid overwhelming information in one illustration. Okay, and then next one would be, so this would be our F1. Okay, so which is F1. Okay, which is again from north 10 degrees to east. Okay, so next one we have here, let me just highlight that so you know it is. Okay, now F2, it's from north 60 degrees to east. So we have here F2. So let's say we have here. So a little bit longer here because we know it's 60 pounds. Compare it with F1. Okay, so that would be our F2. Okay, so next, let me just go ahead and draw parallelogram here. Exactly the same as F2. Okay, and then exactly the same as F1. Okay, there you go. Okay, so therefore, our resultant vector here would be this vector. Okay, so this would now be our resultant vector. Let me just go ahead, or I'll just be writing it as F, so it would be uniform here. Okay, uppercase F without those subscript. That means to say our resultant vector. Okay, so now in this case, what we want here is the angle for the resultant vector would be this angle right here. Okay, which is in the standard position. Okay, that's the angle that we want later on. Okay, so now, so what we're going to do is first we are going to solve, or we're going to write F1 and F2 in an I and J equation. Okay, in terms of I and J. Okay, so let me go ahead and start with F1. So F1, so that's gonna be the magnitude of F1, and then cosine angle theta, and then that I, and then we have here plus F1 sine angle theta, and then J. So we have here the magnitude for F1 is 30, cosine. Okay, so now you have to remember this 10 degree here, it is with respect to the y-axis. Remember, this angle right here, it must be in standard position. So if this angle here is 10 degree, then therefore the angle on this side right here would be 80 degrees, because we know the total measurement here is 90, right? So that would be 90 for the F1. So that's gonna be the magnitude, sorry, not the magnitude, but the angle for the F1. Okay, for the angle of the F1, that's going to be 90 degrees minus the 10 degrees. So that's going to be 80 degrees. Okay, so we have here cosine 80 degrees. So plus, again, 30 sine 80 degrees, and then J. All right, now I'm just going to go ahead and approximate this, okay, since we know that 80 degree has nothing in the special right triangle. So we have 30 and then cosine 80 degrees. So that would now be equal to 5 point. I'm just going to go ahead and use 2 decimal place here. And then I hat plus, okay, 30 and then sine 80. We have 29.54 and then J. Okay, so that would be our F1. Okay, so now let me go ahead and move on with F2. So F2 has exactly the same formula here. It's just that, of course, the magnitude here must be the F2 here. Okay, so the magnitude is 60. So that's going to be 60. And then cosine. Now, we know that this is 60 degrees. Okay, but like I mentioned, similar with F1. So the F2 angle here must also be subtracted from 90 because what we want there is the angle that is in standard position, okay? So minus 60 degrees. So that's going to be equal to 30 degrees, okay? All right, so now we have a 30-degree angle here plus the 60 sine 30 degrees and then J. Again, I keep on forgetting that part. Okay, so now we have the 60. Oh well, so we have here what do you call this? Oops. Okay, 60 and then cosine. We have here exact value, cosine 30 degrees. If you remember that, cosine 30 degrees is radical 3 over 2. Okay, and so but then since I started with F1, which is an approximation, so I need to continue with the approximation so I can add that with the approximate value of F1 later on. So I will have 51.97 I hat plus 60 and then sine 30. So that's gonna be, oh yeah, this is 1/2. Okay, and then J hat. All right, so now this is now the F2. Okay, all right, so now for the resultant vector according to addition, okay, so all we need to do is to have that resultant vector is equal to, we'll add F1 plus the F2. Okay, so meaning to say that we just need to add the A component plus the B component. Okay, so that's gonna be now 5.21 plus 51.97, so that's gonna be equal to 57.18 I. Okay, plus F2 is where's the F1? Okay, so 29.54 plus the 30. So that's going to be 59.54 and then J hat. Okay. All right. So, okay, so there you go. We now have here the resultant vector with its component, okay, which is the 57.18 and 59.4. Okay, so what's next here? So now we can find now the magnitude of the resultant vector, okay? So finding the magnitude of the resultant vector, so that's going to be square root of the two components, so 57.18 squared plus 59.54 squared. Oops, okay. Okay, now putting everything on your calculator, you must be getting 82.54. Okay, all right. Okay, so this is the magnitude of the resultant vector. However, not just with the magnitude that we are interested with, but we also need to find, of course, the direction of the resultant vector. Okay, so how are we going to find the magnitude of the angle or the direction of the resultant vector? Okay, so all we need to do is to Well, we can use a trig function here, okay, since we already know the, what do you call this? Since we already know the magnitude, okay, of this given site right here, okay. Actually, you can use the tangent trig functions, the sine or the cosine, whichever, okay, you are more comfortable with, that's fine, okay, you can always use that. Okay, so in my case, since we are looking for an angle that is with respect to the y-axis, because remember, we are going to not this angle right here, because once we are going to write it in a direction form like this, the navigational form, then we need to do it from north and then going east, okay. Now if I'm going back with this form, okay, so how we visualize my plan here is that I'm going to create a right angle, a right triangle, okay. So as you see here, so it's like creating a right triangle here to find this angle right here, okay. Anyway, because we already know the horizontal component of f. What is the horizontal component? It's 57.18, okay. And then we know, okay, we already know the resultant here, which is the 82.54. And actually, we also know the, what do you call this? The vertical component, which is the 59.54. So like I've said, whichever sine, cosine, tangent, okay, whichever you want to use, okay, that's fine. Let me go ahead and use the, okay, the cosine, okay. So let me go ahead and use okay, so let me avoid this one. Okay, I'll go back with this two, okay. Okay, let me just go ahead and use a tangent, okay. Opposite over adjacent, okay. So tangent theta is equal to opposite is 57.18 over the adjacent is 59.54. Is it 54? Yeah. Okay. All right. Now, to get the angle here, we should be getting the inverse of tangent. So 57.18 over 59.54. Okay, so let's do that using our calculator. So now we have, okay, shift tangent, we have 57.18 over 59.54. Okay, so what we have here, as you can see, we have 43.84. Okay, so let me go back there. 43.84 degrees. Okay. Okay, let me just use another, because I use angle alpha here. Let me just go ahead and use another, let's just, let's say angle alpha here. Okay. All right, so there you go. We now have here the directions. Okay, so let me just go ahead and write the direction of the force here. So we have the magnitude, the resultant factors of the magnitude here would be the 82.54, and then the direction would now be equal to, from north, 43.84 degrees to east. Okay, so this would now be our magnitude and this would now be the direction. Once again, if you want to find the angle here, all you need to do is to subtract that 43.84 from 90. So that's going to be equal to 46.16 degrees. Okay, but like I've said, that is not the angle, which, well, in this case we want the direction. Okay, so however, the problem is wants you to write the direction as well. If they want you to write it in this form, then you have to give it the angle with respect to that north or south. Okay, But if they are just looking for that standard form of the angle theta, then this is the angle that we want, okay? All right, so that's everything it for the last example, okay? So once again, it's your turn to complete the checkpoint problems here. Please try graphing the vectors, finding the magnitude. What else we have here? Computing the products here, and then also determining the unit circles. Okay, all right. Okay, so there you go. That's everything it for section 6.6. Okay, now as for, okay, so today we have learned to represent the vectors, perform operations with them, and then find the magnitude, and then determine the unit vectors, and solve application involving forces and motion. So again, these ideas will prepare us for our next section, which is the dot product, which is a section 6.7. Okay, all right, so once again, I'll see you. Thank you for watching, and I'll see you in the next lesson.